Doing today's introduction is Dr. Patricia Pavier. She is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Work Group. Patricia.
Thank you so much, Bertha, for the introduction. And yes, Dave, you're on. It's a pleasure to have you today with us. Dave is a distinguished member of the technical staff and distinguished inventor at Oak Ridge National Laboratory. He currently represents the U.S. and serves as the vice chair of the Provisional System Steering Committee for the Gen 4 International Forum on MSRs, chairs the American Nuclear Society's working group developing a design safety standard for liquid fuel MSRs, and provides technical oversight of DOE's university project on MSRs. He is a past chair of the American Nuclear Society's Human Factors, Instrumentation, and Controls Division. He has been a staff member at Oak Ridge for more than 25 years and is currently a member of the Reactors and Nuclear Systems Division. He has, in the past, served as the Oak Ridge team lead for space reactor instrumentation as part of the Jupiter Icy Moons Orbiter program. Since 1995, he has served as an adjunct assistant professor at the University of Tennessee, Knoxville, in the nuclear engineering department, and is a current member of the Nuclear Engineering Program Advisory Board for the Ohio State University. So without further ado, I give you the floor, Dave. I thank you very much for volunteering and presenting this webinar. Thank you so much.
You're more than welcome, Patricia. Well, welcome everyone. The topic we already had, which is my perspective on safety evaluation methods for molten salt reactors. I have to start with the sort of the disclaimer on here that while this is my perspective on safety analysis, this is not necessarily the perspective of the U.S. Department of Energy or the U.S. Nuclear Regulatory Commission. Perhaps it should be. Well, to get started with, why do we need this? Well, basically, efficient and effective safety evaluation is critical to reduce the financial risk for investment in MSRs. Right now, MSRs are transitioning to being commercial devices, and they need substantial amounts of investment capital. Significant time and resources are required. The existing LWR-centric framework would be really difficult to apply because the characteristics of molten salt reactors and light water reactors don't match very well. And there are currently multiple initiatives to modernize advanced reactor licensing. Liquid-fueled reactors, however, are distinctive even among the Gen 4 nuclear energy systems. In the box, you can see the goals for Gen 4 nuclear energy systems. And in the second one, you can see a low likelihood of reactor core damage. So even among the Gen 4 systems, we still look at things like core damage, which really doesn't make sense for a liquid-fueled reactor on there. So we really have to look at how do we go ahead and align safety evaluation with the actual characteristics of the reactor as opposed to the characteristics of other and solid fuel reactors. Now, keep in mind, however, that liquid-fueled reactors are not new. Say, all the way back in the time of the Manhattan Project, two of the Nobel Prize winners there argued that we should be using liquid-fueled systems right from the beginning, and some of the first critical devices were done with liquid fuels. So this isn't a Johnny-come-lately technology, it's just a very different technology. Okay. Start with U.S. federal law really doesn't say how do you demonstrate adequate reactor safety. Instead of being that prescriptive, it goes ahead and delegates the authority to the Nuclear Regulatory Commission. The Regulatory Commission has issued 2 guidance documents recently, Reg Guide 1.232 and Reg Guide 1.233, supporting commercial advanced reactor safety adequacy assessment. Overall, both deterministic and probabilistic methods remain acceptable methods for demonstrating adequate reactor safety. The methods remain based upon, okay, you develop some principal design criteria, identify licensing basis events, classify your system structures and components as safety related, non-safety related, and then consider the defense in depth against accidents. There's an alternate safety evaluation path available for non-power reactors. That's in NUREG 1537, where the safety adequacy is based upon limiting effects of postulated maximum hypothetical accidents. There's an MSR specific version of this currently under development. Safety analysis is a required part of licensing, but it's not all of licensing. Licensing has a lot to do with the financial and the environmental impact and stuff in addition. But commercial nuclear power plant safety analysis requires an applicant to provide sufficient information to the NRC to reach a conclusion of reasonable assurance of adequate protection of the public and the environment. Basically, the NRC safety goals are no significant additional risk of life and health and no significant addition to other societal risks. So we go ahead and we need to look at what is the risk of building and operating the plant. Well, the risks for a nuclear plant are exposing the public to radiation. So the basic primary safety function for any reactor is avoiding the release of radionuclides. It's the basis for NRC's quantitative health objectives. It's in Title 10 of the U.S. Code of Federal Regulation. It's Part 20 provides some specific how much you can release to the general public. There are a couple of supporting safety functions because cascading accidents are possible, and that's control the reactivity and reject the decay heat. Because if you fail at either one of those, you're going to start releasing radiation. Safety analysis starts by developing an understanding of the plant and a design and the operation. What are the intended functions of the plant system, structures, and components? How do the requirements change for the operating state? For example, if you're doing maintenance on a molten salt reactor, you've opened up the outer containment. Well, you've got things like the cover gas system, which is right in there. And if you opened up the cover gas system while the containment was open, you have a direct access path for a lot of noble fission products, which would be a very significant release. So you have different rules based upon what are the different state that the plant is in, whether it's in refueling, maintenance, decommissioning. A preliminary hazard analysis is where you sort of start. You get a basic understanding of what can go wrong. Where are the radionuclides? Where are the energy sources on there? What's the potential energy? You've got stored high pressure. You've got reactive chemicals. Oh, gee, I've got cooling water somewhere near a hot thing. I might get a steam explosion. What are the relevant common and external hazards? If there's a fire, there's a flood, there's an earthquake, there's a blackout, just basically break the system down into small pieces and look at what can go wrong with it. Deterministic MSR safety adequacy stems from the current LWR licensing pathway. Essentially, you take the LWR general design criteria, which are in 10 CFR Part 50 Appendix A, and then you apply there to advanced reactors. Well, Reg Guide 1.232 does this. It creates some advanced reactor general design criteria, which are largely technology independent, but it doesn't really go into the specifics of what is required for an MSR, because an MSR is not a generic reactor, it's a specific reactor. And so, but Reg Guide 1.232 does include specific criteria for both sodium and high temperature gas cooled reactors. Well, as a result of this, the American Nuclear Society has been working in Working Group 20.2, is attempting to formulate some MSR specific design criteria. Right now, we have to include some substantial conservatism in the initial version just because we don't have very much operating experience, very limited operating experience. And unfortunately, significant time and effort was required to develop minimum acceptable design criteria for HTGRs and SFRs, even with their much greater degree of experience on this. So we may come up rather rapidly with a rather conservative set of design criteria, but then if we could go ahead and get a minimum set, it'll probably take some more time. Probabilistic MSR safety adequacy is based upon quantitative accident and risk modeling. It's a data-driven approach that provides high-fidelity understanding of nuclear power plant risks. Essentially, it gives you a rational basis for making decisions about what's safety unacceptable and what's acceptable. Unfortunately, MSRs have much less reliability or accident progression data than other advanced reactors, making it more difficult to apply a data-driven model. They've got much more diverse potential configurations than other advanced reactors. If you look at things like, direct contact of the fuel and the coolant in the core in some people's designs, or you have PRAX, DRAX, RVAX type decay heat removal systems. No other reactor class has as diverse a set of configurations, with possible exceptions of water reactors that include things like aqueous homogeneous water reactors. In addition to that, the reliability of passive safety systems, particularly ones that include moving coolants, has been proven to be more difficult to quantify. We just don't have proven methods for some of the passive safety system reliability quantification. They're under development, but the progressive and partial degradation, which is characteristic of these, it really doesn't align with conventional PRA techniques. The advanced methods, which do exist, haven't yet undergone regulatory scrutiny. Things will be better once they have matured a bit. The existing regulations provide an alternative pathway for safety adequacy assessment for advanced reactors. There is actually, in the traditional links, 50.43E indicates that reactors that use simplified, inherent, passive, or other innovative means would only be approved for their safety functions if performance of each safety feature has been adequately demonstrated, interdependent effects among the safety features have been demonstrated to be acceptable, and sufficient data exists on the safety features. Analysis, test programs, experience, or a prototype reactor can be employed to acquire the required information. So you've got another path where you might be able to build, for example, a prototype reactor that operates at reduced power or with additional safety features initially, until you've acquired adequate data to provide a reasonable assurance of adequate protection. Unfortunately, MSRs are going to require some additional safety performance to go the 50.43E route of demonstrating adequate safety. So evaluating risk is the central component of a nuclear power plant safety analysis. And risk is the possibility that something undesirable will happen. Well, what can go wrong? What are its consequences, and how likely is it? That's sort of how you determine what the risk is in a quantified manner. Well, defense in depth is a primary mechanism for us to accommodate what if we are wrong. Because if we don't have the evaluation correct and something unexpected happened, well, we put another layer and sometimes another layer to go ahead and accommodate the fact that we remain uncertain about things that are new. Well, functional containment is another concept which has recently been approved for all advanced reactors. And functional containment essentially is actually apply the physics of the system entirely to containment, not just the bulk barriers. So so if you look at how that works for an MSR, basically you've got multiple layers, some of which are not normally stressed. So so you've got pretty good ability of inspecting them. It's very difficult at the moment to inspect the salt-wetted barrier simply because of the radiation field and the harsh environment. The barrier performance requirements depend upon their safety function. So if, for example, the drain tank containment system, which is a separate cell, needs to contain the fuel when it's not critical, but it doesn't have the same requirements about being containing it during a critical system. And part of the way that the functional containment sort of conceptually works is almost like a hot cell facility, where you've subdivided things both by layers and individual cells and into separate cells, so that each one can be considered separately. So it's a segmented system. And then the independent barriers. One of the nice things about MSR, because of their low pressure system, and most of the way that the barriers communicate is through pressure relief, so the failure of a single barrier does not substantially stress the other barriers. So this is very much unlike the large light water reactor, where you'd have a large break loco, where you'd immediately get a lot of pressure on your large dry containment. And that really helps to minimize the potential for cascading or escalating failures. Essentially, MSRs have some very desirable inherent safety characteristics. Everything, however, depends upon quality. And quality in all of the design criteria is always the first criteria. I mean, things like, was the design correct? Did you actually do what you thought you were supposed to be doing? Or are the materials correct? Has the plant been operated and maintained according to the plan? And unfortunately, little historical MSR data was acquired under a modern quality assurance plan. So a lot of the stuff that we think we know about fuel salt comes out of the fact that, well, halide salts have a lot of other purposes. They're used in heat treatment and aluminum smelting, and so we've got a lot of historic data, as well as the large historic U.S. molten salt breeder reactor program, but it simply wasn't acquired where we've got the QA tied to it, so that we can really say, what's my uncertainty in there? And that's going to be that's right now presenting a challenge to how do we incorporate this into a fuel qualification plan. MSRs present different safety analysis challenges than other reactors classes. The radionuclides are distributed across the plant. In most reactors, you just look at the core and the used fuel pool, and you basically solved your, well, as long as you watch those, you don't have significant radionuclides. Well, the gaseous fission products in our systems separate inherently from the fuel salt. They're not, the nobles just come right out. Well, that's pluses and minuses on there, because while they come out, you can go ahead and treat them and capture them. So they're in a different location. So they're not available to release during an accident. On the other hand, if you have an accident, the stuff that's in between being produced and being captured, well, that's coming out. And that's a fair amount of stuff. So there's also things like integrated fuel salt processing is possible. Well, the processing system could also have accidents. Also, the salt-wetted components have limited lifetimes. So you end up with an unconventional high-activity waste stream, which presents a safety system, whether it's your carbon, your graphite, or your reactor vessel, your heat exchanger, which have got plated out fission products all over them. It's an extremely high radiation amount that you just don't get in other reactor classes. There's really less and substantially dated operating experience. We've only operated one MSR reactor for a significant period. That was the molten salt reactor experiment, which was about 7.5 megawatt reactor, which operated from 65 to 69. While it did operate quite successfully on there, so we do have some confidence that we can actually operate things stably and successfully with high availability. But we've had no large-scale reactor or component demonstrations, so large pumps, large heat exchangers. We just simply haven't done that. We've never demonstrated a fast spectrum molten salt reactor, and several of the vendors are very interested in exploring the advantages of the fuel cycle that are obtained through the fast spectrum. They're really minimal prior accident performance demonstration. We've never done the equivalent of, pouring large quantities of fuel salt on the floor, which is sort of the equivalent of these fuel melt experiments that we have done for light water reactors and sodium reactors. MSR risks have substantial overlap with those of fuel cycle chemical processing facilities. Simply, we look a lot more like a chemical plant than other reactor classes. Both of these systems contain large quantities of radionuclides without large quantities of accessible high pressure or pressure generating fluid. Yes, we will have a power cycle that will have high pressure fluids, whether that's a supercritical CO2 or a supercritical steam system, but they're separated by a heat transfer loop with rupture disks. And rupture disks are something I have a high confidence we're going to keep the pressure away from the plant. But that difference is a really key conceptual separation between fuel cycle facility and reactor risks. There is a modern set of rules and safety evaluation methods for fuel cycle facilities under 10 CFR Part 70. It's basically used process hazard assessments. It's central to this. NUREG 1513 describes how to perform the process hazard assessment. In that, it's referred to an integrated safety assessment there, but it's a proven method to provide reasonable assurance of completeness for accident identification. However, it doesn't really quantify the risks, so you can't really say, well, are my probabilities of risk adequately low based upon performing a PHA? For that, you would need to use a PRA, probabilistic risk assessment. The original reactor safety adequacy evaluation method was based upon containing a maximum credible accident. Safety adequacy of the first commercial reactors was evaluated with a combination of hazard assessment and containment of this maximum credible accident. That worked well until large light water reactors were developed. When they got bigger, there was a credible potential for catastrophic accidents where the containment did not contain everything. And some of these, because we did not have very good accident evaluation tools, we did conservative estimates of what was going on, and they ended up with really severe potential consequences. And that was a large part of the drive for developing enhanced accident modeling to give a higher fidelity representation of the accident, so we would actually protect against what's going to happen, not some highly conservative, fictitious accident. Well, escalating and the cascading accidents really are a big issue with systems that have a large amount of internal stored energy. However, reasonably designed MSRs lack the historically identified mechanisms that could result in catastrophic accidents. High pressure. Essentially, there's no reason to throw the radionuclides out. They're just sort of sitting there in a pot. And even if you didn't have the cover on it, they wouldn't tend to go anywhere because they're not at high pressure. There's no interaction of hot metals with water. Steam and hydrogen explosions have been of concern since the 1950s or 1940s even. And that it's just MSRs have a very advantageous set of inherent characteristics. So MSRE did employ a maximum credible accident for siting evaluation. It was based upon a dual independent containment layer failure. The failure has a little bit of a caveat on it. The second one of these, what we did was we had a water spill within containment sufficient to induce significant leakage in the second containment layer, along with gross failure of the fuel salt boundary. So basically, they poured the core out on the floor and at the same time put enough steam in the system to go ahead and induce a 1% per day volume leakage on there. And what they actually did to make this really work, they put a large line to a suppression pool and a gas retention tank, which are quite large tanks, so that they would be difficult, so you couldn't build up more pressure, because they did use water cooling both of the cell walls and of the components within the cells. One of the challenges on this is they didn't have any information yet, or very much or proven information yet, on the interaction of iodine with the condensing tank. Turns out if they'd been able to put the actual chemistry and physics on there, they'd had a much smaller accident. But even with this, where they were leaking this out into the confinement on this, their maximum credible accident, where the confinement was a vented confinement because people were around that. And the only way they got a real serious accident was to leave the fan on to actually vent all the things that were coming out into the containments. So you had to actively vent the reactor to disperse the radionuclides. Otherwise, not much would happen other than right at the site. MSRs have a readily apparent high degree of passive safety, and readily apparent is really important because it helps develop confidence in both the regulators and the public that what we're saying is very likely true, that this is true, that there isn't something else going on. And it's a strong inherent retention of the radionuclides. That's both chemically and the fact that they're at low pressure. There's a large margin to boiling on this. There's no way of developing the multi-atmospheres of pressure. There are minimal amounts of water or other phase change materials within containment. And this, we're probably going to cool with gases. Yes, we're probably going to some form of a nitrogen cooling cycle. The power cycle is separated from the core with rupture disks along the piping. The fuel salt contains many of the radionuclides. Some of the really nasty ones, the strontiums, the cesiums, form really stable chlorides and fluorides. However, up to 40% can be released into the cover gas because as you create a fission product, it's not on the stability curve for the isotope, so it beta decays and rebeta decays and rebeta decays. And someplace during that decay path, there often is a noble gas, and those noble gases do not stay in the fuel salt. Some of them will decay before they get there and then will be trapped in the fuel salt. But if they are, once they've decayed, we can go ahead and they've been released from the fuel salt. We can trap them outside of the fuel salt. So there's only an hour, or depends on what your design and your flow rates are, is how much of the fission products that are available to be released in the event of an accident. And many of the other things also that don't bind in there, turns out, are high melt point solids and refractories and noble things that played out on the surfaces are also not available to be released. Another good thing is that the fuel salt's in a low chemical energy state. This is distinctly unlike sodium. It's a low Gibbs-free energy. You really don't interact with the environmental materials. You throw water onto it, well, it becomes more corrosive and you get a steam explosion. But it doesn't do anything like have a fire. Having a low chemical energy state's a useful property. MSR, again, readily apparent degree of high passive safety. Very good negative reactivity feedback. It's about the only fast reactor where, because essentially as the fuel salt heats up, it becomes larger at the volumetric expansion, you decrease the amount of fuel in the core. We've got the fuel is normally kept in its maximum reactivity configuration. There's no fuel consolidation. There's no way of getting these huge positive feedback accidents. There's no hypothetical core disruptive accident. There's a substantial margin to structural damage. Actually, we considered MSRs as prompt burst reactors before triggers were developed on there, simply because they give you a very good, strong negative reactor feedback. MSRs really have the potential for effective passive decay heat rejection. A lot of that starts with the fact they're hot, and it's easier to get, whether it's radiative or convective cooling. Starting with a hot source is easier to reject the same amount of heat from than something which is cooler. But fuel salts have got an advantageous combination of heat capacity, thermal expansion, and viscosity to drive natural circulation cooling. There are no operational cliff edges we've ever had, so it looks like gee, there's no at-whisk, there's no departure from nucleate boiling. Simply, we don't have the features where you're really worried about a fast response. MSRs also retain the potential of containing all credible accidents at any scale. So it doesn't suffer from the same issue that LWRs had when you got big, that really a large containment probably wasn't going to be an adequate response. So avoiding potentially cascading accidents, especially accident sequence that pressurize containment, is a key consideration. An MSRE type suppression pool capture tank system would be quite large for a commercial scale plant, but it's a possible design. I think basically most folks are going to conclude that they don't want to use water cooling, and so if you end up with a suppression pool and capture tank system, it wouldn't need to be as big. The system immaturity really still necessitates some additional conservatism in the design requirements, but to ensure that containment will survive. There's a high degree of passive safety, which will help minimize the additional cost of the system. Reliable quantitative performance data and models would decrease the required amount of conservatism. And so we're hoping to get more data so we can reduce the conservatism in the models. Additional requirements are intended to prevent a single event from damaging all the containment layers. So one of the things that you look at is, like, if you have a core, you probably want a core catcher, so that if you pour the fuel salt out, or a guard vessel, so that you can still continue to remove the decay heat even following a severe accident where you've had a large break within the fuel salt system. We really are trying, not having a cascading accident where you're damaging all the layers is central to being able to maintain credible containment. Assuring that the bounding accidents then envelope all credible accidents is key then to demonstrate adequate reactor safety. You cannot just use really simple, obvious accidents, because there can be synergistic and combinatorial effects in the accidents to say, well, this plus this was actually worse on this. So we need to use things like process hazard assessment to incorporate multiple methods, whether it's HAZOPS or failure modes and effects analysis, layer protection analysis, as well as expert judgment from multiple people with diverse technical backgrounds to develop our accident sequences. It's the same basic process as an early phase probabilistic risk assessment. But in any case, in order to have consequences, which is our definition to release radionuclides out into the environment, an accident needs to rupture or bypass all the containment layers. The high resiliency of MSRs enables the use of rather unlikely postulated accidents. So you say, well, yeah, I'm going to have my large break loca, and in addition to this, I'm going to have my rupture my cooling line to look at my safety assessment. Commercial molten salt reactors, however, are not going to have a single maximum credible accidents like the MSRE, but a series of bounding accidents, basically because we have a lot of radionuclides in a lot of different spots, and you could have potential for environmental or harm to the public from rupturing any of these systems. If you just rupture the cover gas system, that will look different than rupturing the reactor vessel, but both of them could end up releasing radionuclides. In this way, it kind of looks like all the multiple design basis accidents for large light water reactors. The advantageous characteristics of MSRs really lower the plant capital and operating expenses on here. So if you look at, okay, we've got to protect against multiple accidents. Well, low pressure, it's a much lower cost than these large high pressure dry containments. You end up with thin walled metal tanks versus massive reinforced concrete structures. Everybody's designing things below grade these days because of the requirement to deal with to accommodate large civilian aircraft impacts on there. That's just easier done by putting everything below grade. Kind of looks like if you've seen a munitions bunker where you dig a hole in the ground, put a hoop over it, and pile dirt on top. Passive decay heat rejection, not using the power cycle, avoids the requirement to use the power cycle system structures and components as safety related. So if you can confine your safety related systems to the nuclear island, well more than half the plants, if you look at the nuclear islands as a small part of the plant, well, most of that is just according to industrial standard, not according to nuclear standards. There's really a large margin to damage. Reactivity accidents are unlikely to damage the system structures and components just because of the inherent negative reactivity feedback. There's a large margin to fuel salt boiling, so it's unlikely to develop high pressure and rupture things. There's really no equivalent to an anticipated transient without scram in this, and we really no one, despite having a fairly extensive look at this, have identified any accidents requiring a rapid operator or an active equipment response. So it looks like we've got days, and we just rely upon physics rather than upon people. Maintaining low pressures is key to avoiding potential rupture of containment layers. The MSRE substantially reduced its pressure through interconnecting a large tank through rupture discs. Largely that they did it that way, both because it was cost acceptable and because it was built, the aircraft reactor experiment was they actually reused an existing containment even the time they were doing that. And so to avoid building a building, they put a big pipe in another tank. The process physics and chemistry dictate the pressure generation mechanisms. Without a large amount of phase change material, water is the big example on this, or sodium. MSRs lack mechanisms for significant pressure generation. Lack of adequate decay heat rejection could fail all the containment layers without requiring pressure generation. So if you look at, you could essentially melt through everything or just pressurize the atmosphere. Even the air, PV equals nRT, could get hot enough if you can't reject the decay heat. So adequate decay heat rejection under severe accident conditions is required to avoid radionuclide releases on this. And we just don't really have the amount of data that we would like to have on these severe accident releases. A dual simultaneous containment layer failure employed at the provides a baseline maximum credible accidents. Again, the failure is it's got some caveats on it. It is not necessary. It's not the true gross rupture, but it is, stressing that next failure layer, a next layer enough to go ahead and give a significant leak. It's much more conservative than the conventional signal failure criteria. However, the basic physics and chemistry are quite similar for any MSR, and the lack of adequate data has resulted in very conservative source term estimates. Again, as I mentioned, the iodine trapping and suppression pool was unaccounted for. And electricity generating MSRs will have high pressure power cycle fluids connected by a heat transfer loop. So we'll be using rupture discs to isolate the pressure. MSRs currently lack adequate decay heat transport data to provide reasonable assurance of adequate protection for larger systems. So we need to understand well enough what happens under a severe accident that we can continue to provide adequate decay heat rejection. So the lack of this could cause multiple layers to fail, and right now there are diverse types of systems under consideration, whether it's a direct reactor auxiliary cooling system, a reactor vessel auxiliary cooling system, a pool type reactor auxiliary cooling systems. Some folks use drain tanks and guard vessels and core catchers. And because of all these different variants, we really have to understand the fuel salt property very well as the performance of their systems. And demonstrating technologies for adequate decay heat rejection under degraded conditions is a key next step to enable MSR safety evaluation. Qualified fuel salt is also key to reliably modeling MSR system performance. If you look at this, you use you have some accident scenario. Well, the fuel performance tells you how it attacks the barriers and how it reacts to the barriers on this. Well, you only understand the fuel performance adequately by having a qualified fuel to know what is there and what are the characteristics of the things that are there. Does it do something you were not expecting it to do on this? And that's what qualification really is adequate understanding of the fuel performance and able to model its operation both normal and accident conditions. Currently, that's a key focus of the U.S. national MSR activities to develop adequate data to qualify fuel salts. And the NRC is currently supporting activities to define exactly what are acceptable liquid fuel salt qualification methods. Fuel salt data quality assurance represents a potential stumbling block for fuel qualification. As I've mentioned, little, if any, of the historic data was generated under a nuclear quality assurance program. Data has been generated by multiple institutions worldwide, and some of this is historic so that the quality assurance information may no longer exist. Right now, it remains unclear how to make most appropriate use of the prior work. The regulations require appropriate level of quality assurance reflecting the importance to safety, and fuel performance is very important to safety. So basically, we're going to need sensitivity and uncertainty analysis as well as accident progression modeling tools to establish data requirements. So we'll do variations of, okay, if the density changes to this, or if the heat capacity changes to this, do we still get an acceptable accident performance? And then work our way backwards to what does the fuel, what do we have to know about the fuel with what quality based upon its accident performance requirements. But the amount of validation data to go ahead and say, well, we've got this huge sea of data, well, I don't think we're going to validate every single piece because there's a continuum within this data, but we'll have to see exactly how much validation is going to be required. Mechanistic source term methodologies for MSRs is key to understanding containment performance adequacy. The NRC has established requirements for advanced reactors to employ a mechanistic source term. Essentially, performance of the reactor or fuel under normal and off-normal conditions is sufficiently well understood for metamechanistic analysis. The transport of fission products can be adequately modeled for all the barriers and pathway to the environment, including specific consideration of containment. The events considered in the analysis develop the source terms, bound severe accidents, and design-dependent uncertainties. Essentially, it's a bounding accident model for developing a mechanistic source term. Simulation and modeling tools are in practice needed. Yeah, you could do this with all paper, hand paper, but today we really would like to be able to do variations. Well, if I change this a little bit, what's the impact of that? And that's what tools are good for. You first have to provide some initial conditions to start your accident progression evaluation. How many radionuclides are where at the start of your accidents? How much, is this solidified here? So you get things from reactor physics, radionuclide generation, consumption, the fuel, salt, and cover gas motion and heat transfer, auxiliary systems, fueling and defueling systems, salt treatment systems, plate out systems. They're all parts of how do you set up your problem. Then you need to automate this to look at different designs and scenarios, to look at every accident. So then the wide diversity of the configurations. I mean, a PRAC system looks very different than a drain tank system on there. The NRC has reactor physics and hydraulics tools that are suitable to model MSRs. Those things like scale as the reactor physics code and trace as for doing thermohydraulics analysis. But we really need some additional tools to develop radionuclide accountancy, because traditionally we didn't have radionuclides in lots of different places, and so the accountancy of where things are that it doesn't really exist in a proven manner, but there is substantial current activity to develop the tools. Implementing mechanistic source term models in the NRC accident modeling tool, which is MELCOR, is underway. The NRC has been sponsoring this, as well as DOE, in considering what are the accidents and what are the configurations. Distributed radionuclide configuration is a distinctive accident component for MSRs. MELCOR requires further capability extension to accommodate the diverse set of potential configurations. Essentially, how do you describe what the reactor is to start the accident off? You need to have those building blocks in there to allow the stakeholders, whether it's a designer or a regulator or a safety analyst, to be able to evaluate particular designs under specific scenarios. MSR safety adequacy evaluation capabilities are advancing on many fronts. Because MSRs are a topic of current interest. We don't yet have a complete and mature set of capabilities. The preferred method for MSR safety adequacy demonstrations will evolve as experience is gained with the technology. We will be able to do higher and higher fidelity models, which will allow us to decrease design conservatism as we develop more and more experience with the system. We need to continue to advance the fuel salt property understanding, modeling tool capabilities, as well as safety evaluation methodologies. The distributed radionuclide configuration during normal operation necessitates a new material accountancy tool. That we just need to get that validated. Currently, in my opinion, the most significant experimental hole is lack of data to model decay heat removal following a fuel salt boundary rupture. Essentially, under degraded conditions, continuing to be able to model the decay heat removal, we need more data and better tools. And I believe that's all I have, and now I'm open for questions.
Thank you, Dave. Well, questions are coming in. Let's take a quick look at the upcoming webinar presentations. In September, a presentation on maximizing clean energy integration, the role of nuclear renewable technologies in integrated energy systems. In October, we anticipate global potential for small and micro reactor systems to provide electricity access. In November, neutrino and Gen 4 reactor systems. So if you do have questions, go ahead and type those into the questions pane. Here we go. Get this a little bigger so I can see it. So Dave, I'm not sure if you can see the question.
No, I can't.
Since MSRs are low pressure systems, are our vendors still planning to include a traditional containment building?
Well, I'm not going to be able to speak to any particular vendor, but I certainly think that you would design your containment to suit your reactor on this and its safety function. And so things that look like meter and a half thick of reinforced concrete, well, the only safety function I can think that it would have would be if you went above grade and you were worrying about large aircraft impact. So my guess is that most reactors are probably going to go below grade and then not have this reinforced concrete. Though keep in mind, because we don't have the downcomer, which is the water, and the 6 inches of steel as shielding, we will need substantial amounts of shielding between the fuel salt and the environment on there. So we're probably going to have whether it be non-reinforced, big concrete blocks or some form of shielding, or perhaps it's just sand and dirt for shielding.
Thank you. Do you have an opinion about the Thorcon design?
I really can't comment on specific commercial designs on there. I mean, they are implementing a traditional graphite moderated fluoride salt fueled system. The current design has got a drain tank and an RVAX, or actually a series of drain tanks and an RVAX there. But without real evaluation, I just don't have anything specific. I mean, it looks like a traditional fluoride salt thermal spectrum design.
Thank you. What are the potentials of reducing decay heat significantly by removing fission products online?
You do actually get something like a 40% of the short-term stuff. It does go down. The problem is that molten salt reactors are not necessarily small. Some folks are talking multi-gigawatt systems. So if you look at how much, you then have to remove that decay heat anyway from the cover gas instead of removing it from the fuel salt. So you haven't really gotten rid of the decay heat removal thing. You've moved where it is. So perhaps you do it in two different systems. I mean, the ways to decrease the amount of decay heat removal are just basically to make a smaller, get less power out of it, have fewer fissions. But it may be easier to remove the decay heat in two places instead of having a large single system. Those are design variants.
Thank you. In your view, what are the most pertinent knowledge gaps related to the chemistry of fission product bearing salt?
Well, certainly we probably don't understand in fast spectrum systems that have a lot of actinides in them. We worry about are things going to solidify right at the outside of the heat exchanger, or we're going to get played out on this, because we just have not run fast spectrum systems, and a demonstration, essentially a fast spectrum version of the molten salt reactor experiment, would give us an awful lot more confidence about that. Otherwise, the fact that we have run a thermal spectrum fluoride salt reactor gives us a pretty good confidence that we have an adequate understanding of the chemistry of the fluoride salts. Whether we should have more to give us a better design is, of course, we want to have to improve our designs. But we're only talking about the safety of the system, and we have a fair amount of understanding for things like, well, is it going to boil? What is the, what are the heat capacities? Well, in general, we'd like to know more about this to expand our potential range of system designs, but there's not, we've run our prototype reactor, our first of a kind.
Thank you. How important is the risk of freezing and recriticality of fuel salt?
It's difficult to imagine how you're going to freeze fuel salt once it's been run for a while. Simply put, there's a lot of decay heat there. So I'm not really worried about freezing fuel salt that's been run for a while. I'm also not really worried about recriticality too much in a low pressure system. It's, we may even, safe shutdown might, be critical at low power. We even define safe shutdown so much in a molten salt reactor. It might not be the same thing in a light water reactor. Part of this is we have such good negative inherent reactivity feedback mechanisms, whether it's spectral shift or thermal expansion. There's nothing like a departure from nucleate boiling accident to say, well, going critical is likely to cause an offsite dose or a damage to components.
Thank you. Is molten salt safe to handle in an experimental look?
Well, I mean, if you go ahead and molten salts are hot, I mean, that's their primary hazard on there, because in order to get molten, none of these things melt. Some of the chlorides melt as low as 400 C, but most of these things melt at around 450, 500 C, and we're running them at 700, 800 C. This is very thermally hot, so I'm not going to say anything that's hot, and it's got a high heat capacity, so it'll transfer a lot of energy. It's particularly safe there. I mean, our big challenge is keep everything dry on there. So in many ways, the challenge is from the stuff on the outside, because the salt can become very corrosive if it gets wet on there. If it's not, actually, if it gets even a little tiny bit wet there, it needs to stay quite dry to continue to have be in a reducing condition, so it doesn't oxidize the container components on there. No, and as far as can you handle, uranium, fluoride.
Oh, Dave, I think we lost you.
Yes, we did.
Dave, check it.
Well,
there
uranium is a natural product. You can look at what its decay. Hello?
Dave, I think your mic might be intermittent. Did you disconnect a little bit?
I'm still here. I have not seen it.
Okay, now I can hear you. Sorry.
Do I need to repeat the last one, or is there some problem?
Yeah, I think you broke off midway on the last answer, so perhaps that would be best to repeat.
Okay. Is there anything especially unsafe about handling molten salts for an experiment? Biggest challenge is they're hot. Being at 100, 800 C and having a high heat capacity is certainly something which could give you pause about what can you do for safety. In addition, if you are looking at a fuel salt, you'll have something like uranium in it. Uranium is a radioactive material, but it doesn't become more or less radioactive by being in a fuel salt. So if you have conditions for handling uranium in another form, you likely have the conditions for handling uranium in fuel salt. I suspect transuranics and other actinides have got their own safety issues, and you'll need to deal with those. But most of the chemistry is not dependent upon the radioactive nature of the fuel, so you can use non-radioactive surrogates as say cesium that's not radioactive. You put that in instead of cesium that is radioactive.
Thank you. There's a question that's kind of a follow-up to one that you've just answered a bit ago. Do you think there is a case for arguing that recriticality preventing freezing should actually considered a positive safety factor by regulators?
I mean, eventually you have to, deconstruct the plants. Eventually you have to things. But I mean, the fact that it stays in a stable condition for a very long period of time, again, the only thing that you really worry about is, are you going to release the radionuclides to the public? Otherwise, your plant owners want, hey, don't destroy the stuff inside. We want to generate power on this. So I don't think that there is something inherently wrong about maintaining the plant in a low power critical configuration for a very long period of time. That doesn't seem to have, to cause a release of radioactive material into the environment.
Thank you. Has there been a cost analysis of the MSR to determine its economic competitiveness?
There have been a number of analyses. The problem is what the assumptions that go into them and what to believe in them. Some of the analyses look very favorable to the point that it is unwise to go ahead and consider, essentially we get painted by.
People are working from home.
As by being, unduly optimistic.
Thank you.
What
experimental facilities are needed to validate safety models?
Well, one of the things, I think Argonne National Laboratory has a pretty nice setup for essentially doing the equivalent of a fuel salt spill, because it's their natural decay heat removal facility, which looks like their RVAX facility they've got. And so that's our I think is our biggest thing right now, is being able to, I do not believe that we're going to be able to say that a large fuel salt spill is adequately unlikely that it will not occur. And having that large fuel salts, and therefore we have to be able to show we can maintain adequate safety following that fuel salt spill. And so most of that is decay heat removal and, well, criticality as well for fast spectrum systems that have a large content of fissile material. Both of those are handled classically. Lots of absorber around, unfavorable geometry for criticality, and continuing to look at, well, have I developed a fog or a mist so I don't get adequate radiative cooling? Do I get a crust on this? Does it freeze on the bottom surface so it doesn't flow anymore? The classic types of things, and those are done with accident type facilities, and fortunately the US has already invested rather significantly in parts of those. It's just that there has not yet been the interest and the investment for a long time to apply them to molten salt reactors.
Thank you. So, general question. Are there uncertainties at this time that may impact the DCA if a given MSR reactor design was submitted today? For example, are there uncertainties in reactivity control that impacts a regulatory position?
Well, certainly the if you are trying to go ahead and say what's my reactivity control mechanisms, that I am aware of, none of the reactors are designing their active reactivity control systems as a safety-related system. So they are entirely intending as a passive systems for safety purposes. What does that mean? Do we know adequately that we would not get recriticality? Probably not. There are some possibilities of doing plate outs, particularly in fast spectrum systems where we might get a criticality. Question becomes is if we have an unplanned criticality, what are the safety implications of doing that? And that is where molten salt reactors really shine. Because there are not people nearby. And it's within a highly shielded environment because during normal operations, it's supposed to be critical in there, and you have to have the shielding to deal with the criticality. There are a number of potential accidents like filling accidents where you leave your filling pump on too long. And that ends up with an excessive criticality, which ends up melting the reactor vessel, which ends up pouring things on the floor. So the entire accident chain sequence, do we have adequate information to deal with the entire chain sequence? No. And some of this starts with having more power generation than you wanted to. So that's involved with criticality. But as far as a prompt feedback, we don't really have much issue about a rapid response, response negative reactivity insertion requirement.
Thank you. What's the approach to dealing with the waste salt at the end of the life cycle?
Well, largely, most of the reactor folks are saying that we don't have waste salt because the salt doesn't accumulate radiation damage. And we essentially reach an equilibrium amount of fission products as stuff burns in and burns out on there. And if you read some of the papers that Terrestrial Energy has done, what they're doing is saying is we start with a fuel salt with about a 2% enrichment, and then we refuel for 7 years, and we add volume to this fuel salt over time. And then what we do for our next reactor core is we split this over time into 2 different reactors, and we use this as a means of breeding or creating fueling our next and our next and our next generation of salts. That doesn't eventually get rid of the waste salt, because eventually people will stop using molten salt reactors as a reactor class and everything becomes waste at once. But that may be perhaps it's 1,000 years from now before we end up with creating our first major fuel salt waste. And so most folks are saying, well, we just keep reusing the fuel salt on there because it doesn't radiation damage like like solid fuel on there, just because it's a liquid. And so it's a matter of how much do you accumulate in it. And it turns out after 60, 70 years, you end up with an equilibrium amount of radionuclides in there where you're burning things out and breeding things in and decaying things all together. So our challenge is on the waste tends to be things like, well, gee, I have a heat exchanger. I had a little bit of a heel, and by the way, a whole bunch of stuff plated onto it. And so I've got this heat exchanger, which is extremely radioactive, and it only lasted 20 years. And so if I have a 100-year plant on here, I've got 5 of these I got to deal with. So I've got an unconventional, really high activity waste stream, but it's not so much a fuel salt waste stream.
Thank you. What kind of new radionuclide material accountancy tools are under development?
Well, there are several of these that are being supported from the Nuclear Energy Advanced Reactor, the NEAMS program, as well as through the MSR National Campaign. And there's a Modelica-based tool there where it's essentially it's called Transform is the particular name of it. There's also some efforts to implement this into SAM, which is another one of the NEAMS tools. And it's basically a model of process physics and chemistry, and then interface with the domain-specific codes, scale and the like. If you look at, I think the leading effort on there on a practical basis is the Transform tool being done by the U.S. National Campaign, MSR campaign.
Thank you. Do you have a qualified thermohydraulics code for MSRs?
Well, trace continues to have molten salt properties within it, but it doesn't have a wide set of molten salt properties within it. And certainly we would like to expand the number of molten salt properties within it. But that's not so much, that's the traditional, that's the type of system. But once you have the properties, you can put it into almost any thermohydraulic code. So there's not Cobra or something, but it's a matter of having the right properties to stick in. And we are developing properties, and but so my answer is that trace exists. It has a limited set of the thermophysical properties in it. And that will probably be used for a lot of the accident progression modeling. But otherwise, this is a single-phase heat transfer problem, sometimes with a little bit of bubbles. But single-phase heat transfer with a fluid is not, really exotic, heat transfer problem.
Thank you. Similarly, the next question is neutronic codes and neutronic codes and thermohydraulics codes and thermohydraulic codes exist to compute MSR, but what about chemical fields?
Well, if you are trying to do a design of a fuel processing system, you'll need to understand things like how many stages of extraction and elements of that. Otherwise, large of this comes out of composition and gives free energy. And this, we have what are the things you need to know in a chemical field? Some of this is, if you want to process the fuel, then you'll have to know additional information about this. Otherwise, what we really want to know in a chemical sense typically is the fissile material going to plate out, and that's a solubility question, which we establish some bounding parameters on. And have you kept it into a reducing environment because fission is an oxidative process, so we have to keep overall things in a reducing condition so that we don't cause excessive corrosion. And typically what we do is we actually monitor the corrosion of the most sensitive component in the boundary material. It tends to be chromium. If the chromium composition starts going up, we just we add a little bit more of a reducing metal. What we were doing in Flive salt was contacting with beryllium. So it's more Edisonian than a first principles knowledge of this. And so question is, how much do you need to know the fundamentals to operate a reactor? I make the point that understanding the fundamentals is good for advancing the designs and advancing things, but probably not necessarily for safety evaluation of the reactor.
Thank you. This question reads, in MSR, there's no cladding. In addition, operation will probably involve online extraction of gaseous fission products, lanthanides, etc. Thus, how can we define a first safety barrier?
Well, you're correct. There's no cladding on this, and the fission and the gases have almost no solubility in the salt. There is a limited trapping in the carbon, and so, but there is a first boundary. Essentially, it's the reactor vessel and the cover gas system on there. We will, and that will, certainly the cover gases will come out. The fission gases will evolve out. You'll probably either use a scrubber or a trap system, and then a series of carbon beds to get essentially to hold the fission gases for decay, and eventually you'll bottle the Krypton 85. We get way too much Krypton 85 to be able to vent like LWRs tend to vent some of the fission gases, just because there's a little bit, because most everything is retained in the matrix or inside of cladding, and it's only if there's a leaker it comes out. Well, essentially all of ours come out, so we have to bottle So, the barrier is is the stuff where, the first barrier is the stuff where under normal operations there are radionuclides inside, and there under normal operations there's not radionuclides outside. So that's a pretty simple definition.
Thank you. How's the molten salt manufactured and delivered to the site?
Good question. Making fuel salt is an interesting issue which is not entirely resolved. Certainly, some of the methods, for example, Kairos, which is not a liquid fueled MSR, but it does use molten salt, would be getting their flied salt from a particular vendor and just shipped to them. And the methods for manufacturing lithium fluoride and beryllium fluoride have not changed. You can look at the historic techniques done in the 1950s, a number of reports on that, and then it's classic chemical processing. And Flibe has announced a partnership with Materion, which is our largest beryllium supplier, for making their salt. But one of our real challenges is that there is not a supplier pipeline. It is not obvious who vendors are going to be able to buy their fuel salt from. And is it going to be developed? Is it going to be shipped as probably as a solid block? Or are you going to ship it where the actinide portion of it is shipped separately? Because you could start up your reactor with barren salt where it wouldn't be critical initially, but it would be hot, and then you would put in a concentrate of salt. Or you could get something where it is 99% of criticality, and then you just put in a little bit more to get to critical. There are just a number of different options for this. There have been a couple of companies, including one which has got an organic route for producing uranium chlorides as a different chemical process, things which have announced that they are they're embryonic companies going into business. This is not a resolved issue on there, and nor are even things like standards for trade. Things like, well, if you get salt, how much oxygen was in it? How did you measure that, and how did you establish this? Because there are very different corrosion performance based upon what are the content of that actual salt. And then if you get to somebody who wants to do things internationally, you make things much more complex, because all the ownership of critical materials about being transferred and transported as to who owns what when and who is responsible for it gets very much more complicated. And so this is exactly how the fuel salt gets delivered and removed, is a significant unknown in the future of MSRs.
Thank you. For effective decay heat removal under accident or off-normal conditions, for example, salt drains into the tank, what is the target delta T for the salt? Is the intention to freeze the salt, simply lower it significantly below operating temperatures? I think some of this you've addressed.
Okay, well, I mean, long term, eventually salt freezes, but I mean, if you look at things where there's a lot of decay heat in the salt, and and that depends a lot upon things like a high power density reactor. Some of the fast spectrum systems are talking 300 megawatts per cubic meter type power densities. This is, there's no way this is going to freeze in a reasonable time frame here. And so there's not a single answer to that. And because it depends upon the reactor design, it depends upon mostly its power density. It depends upon the time frame. Are you trying to? Once if you froze the entire batch of salt because it's then all below 450 C, well, certainly nothing's going anywhere on there. And if you were intending to ship this to the next reactor site, well, probably that's what you want to do. So we're not, all we're trying to do in a short term for a safety evaluation is get to the conclusion of the accident. Once you've gotten to the conclusion of the accident where you are, you're safely, the things are not going further south, where you're removing the decay heat reliably, the criticality is controlled, and the radionuclides are controlled, then you've achieved what you needed to for the safety purposes. What eventually the plant wants to do with the salt later is then a separate issue.
Thank you. There's two that deal with GDCs 25, 26, and 27. So specifically, are GDCs 25, 26, 27 applicable to MSRs? How might the MSR vendor address these GDCs? And then GDCs 25, 26, 27 are generally about reactivity control, redundancy, and diversity in system design of the reactor.
The answer is what we may have to do initially on reactivity control, because there's a requirement to have two methods for reactivity control, one of which involves rods, and those continue to exist in the advanced reactor design criteria, is we may have a near-term and a short-term and a long-term answer on this, because that's part of what we're saying in the ANS 20.2 is what's an adequate response initially to get a license, because it's not incredibly difficult to do a control rod system with a reactivity feedback system to provide negative reactivity control in this. And so it may be that first generation plants have a reactivity control system which is considered safety grade, simply because we have not provided adequate evidence that the inherent reactivity control is adequate. I can't comment on any specific design because I don't know what the design is and how they are doing the design criteria. I indicated that normally what you do initially is put additional conservatism in your design, and then you decrease the conservatism as you get better understanding of the physics. So indeed, reactivity control may involve a short-term component in the first generation of designs that I suspect is as we develop additional models and additional confidence in the performance of the reactor, if you can show adequate confinement of the radionuclides, if you can achieve the safety functions without this, you can make a credible argument that you don't need them. But that's another argument you have to make. And do you want to get your plant built today, or do you want to get your plant built after you've gone through having an argument about an exception?
Thank you. Would you explain DEC for MSR?
Design exception conditions. The design extension conditions, essentially. Well, if you look at where what the ACRS has recently been saying is that for some of the advanced reactors, the design extension conditions and beyond design basis accidents are sort of a continuum. And they don't really stand out so much from from design basis accidents there. And so I'm not sure that we've got a defined set of particular accidents for a particular plant. So I don't know that our beyond design basis or design extension conditions really are much different than what you would have as a bounding accident. But I'd have to get I think this might involve some significant more discussion. So I don't think I've given a very satisfying answer to that.
Thank you. Has it been demonstrated that denatured thermal MSRs can guarantee a negative temperature coefficients in operation and casualties with much higher fertile and fission product poisons to HELEU or especially LALEU fissile ratio than MSR. If I post it, you'll be able to read it better. It's kind of long to read out loud for you.
Well, okay, yeah, I need to go ahead and I didn't get what the question really is.
Do you see it now that I've posted it to all?
Posted it, okay. What I see is noble metal fission played out in the heat exchanger is inlet is identical to the thermal or immediate spectrum fluoride as far as the spectrum as far as the fast chloride MSRs, unlike was stated. Played out thickness is proportional to power and inversely proportional to the heat exchanger tube entrance surface area. It's the only thing I had to say about whether played out is it isn't that is that solubility is different in chlorides and fluorides. Chlorides tend to have high degrees of solubility. So played out does have something to do with with the chemistry on there, and fluorides and chlorides are different. And you're correct; it doesn't have to do with the the amount of production is proportional to power, but whether it plates out has to do with what's the solubility. Has it been demonstrated that denatured thermal MSRs can guarantee a negative temperature coefficient in operation and casualties with a much higher fertile and fission product poison, with much higher fertile and fission product poisons to HALEU, especially low assay LEU fission ratio than MSR? I don't understand. Has been demonstrated that denatured thermal MSRs. So the denatured thermal MSR essentially has a large amount of either even isotope plutonium or U-238 or non-fissile uranium, can guarantee a negative temperature coefficients in operation. And casualties with a much higher fertile and fission product poisonings to HALE. I don't have an answer for that on this. I don't know a specific whether specific reactor physics questions have been answered on there. So I don't have a specific reactor physics response to whether fertile and fission product poisons and I don't understand the part of it than MSRs in there.
Thank you.
Yeah, and it says most thermal MSRs do not assume indefinite fuel life and reuse, at most 7 or 8 years. Well, certainly some of the vendors are indicating that you can, terrestrial being a leading vendor. Only chloride has infinite life and near 100% burnup. And not all fast chlorides. Some use feed and bleed once through. Indeed, that's true. True that some thermal spectrum MSRs are intending, to continue to use fresh fuel on there, and then they have a waste form on there. But one of the leading candidates is to use is an infinite life system, and that's the terrestrial design. In the waste forms for fluorides and chloride salts are still, that's a topic of discussion, and in terms of adequate stability and emplacement, it's in some ways similar to the questions about storing of actinide materials for any other reactor class.
Is the impurity level in the fresh fuel salt specified?
It should be, and there's a question about that as to whether it actually is, and how do you verify that what the impurities are in there, because certainly some impurities have very negative performance aspects on them, and just measuring things like how much oxygen is in the fuel salt is non-trivial, and there hasn't been an accepted ASTM practice that this is how you do that. That's one of our challenges.
Thank you. There's two regarding thorium fuel. One asks about advantages for using thorium fuel. I guess that's the same question. It's just posted twice. I apologize, Jason. It was posted twice. I think there was a little bit of lag in the time you initially asked it.
Well, to me,
does thorium fuel have any advantages? Is the question.
Well, I mean, the reason people are interested in thorium is to substantially extend our fissile resources. The challenge, of course, is remains the same as what it always has been, is that you end up producing U-233, and U-233 is a fissile material. If this is not, and we have to be able to produce it in a manner which is compliant with the Part 74 and Part 75 of the Code of Federal Regulations about material control and accountability and proliferation and safeguarding. President Carter's words about the fuel cycle remain in the presidential directive, which indicates that we will direct our resources to fuel cycles which do not involve direct access to weapons usable materials, remains in effect. And provided the thorium fuel cycle continues to have that as a potential feature, we won't, we will continue to be compliant with the presidential directive. It'd be wonderful to have, increased use of fissile resources, and that's why people are interested in thorium. That and that you don't get transuranics in the waste stream. In this, and not having transuranics, substantially shortens the amount of time you have to watch the waste. So yes, people are interested in that. No, it's not inherently, an element of molten salt reactors.
Thank you. Looks like there's about 6 more questions. I know we're about 30 minutes into this, so bear with us. We'll see if we can run through these quickly. Is there any experimental data or study on molten salt corrosion effect on thermal hydraulics? Is there any experimental data or study on molten salt? Oh, it just repeats.
Well, essentially, corrosion, will of course impact, thermal hydraulics. Essentially, you change, whether you've got corrosion products plating out in places, you're going to change the tube diameter. You're going to change tube diameter. I mean, you also change smoothness. I mean, if you look at things like nickel is really problematic on there. If you go ahead and you take a non-oxidative corrosion where you take nickel out in the hot part and then deposit it in the cold part, nickel tends to grow dendritically, which means you get something that looks like steel wool in your cold part of your loop, and which has, of course, has substantial impact on your thermal hydraulics. If you run even things to reducing, you'll get the fuel salt will attack carbon. You will get uranium carbide formed, and well, of course, that'll affect your fissions. That'll affect everything. By running things to reducing. So this has happened in other cases, but generally speaking, the considerations of corrosion have dominated the impact on thermohydraulics. Other than the potential, some folks have done some studies indicating that we've deposited films on things which have decreased some of the heat transfer, but I don't think there was enough systematic study of that.
Thank you. Do we have good corrosion-resistant materials ready for use in MSRs?
The materials, essentially, we determined if you run the salts in a reducing condition, and that they're not highly corrosive from an engineering perspective. That means that most of the materials are generally acceptable for their service. That does not mean we have an optimal material set. It means that we care about the chemistry a great deal. We also, I don't believe, with a thin-walled system with the radiation damage that you're likely to see, are likely going to have a capability of guaranteeing that your reactor vessel is not going to fail in a manner in which we have light water reactor vessels are just postulated not to fail. I think that we are likely to have failures, potentials for failures at points where you would have leaks. But as far as will stainless steel 316H adequately perform with a reducing salt environment? Well, it generally is pretty darn corrosion resistant. There's not an enormous speed. I start worrying about erosion if you've got a high power density reactor and I'm flowing and the velocities get to where you have in a light water reactor where you're talking 17 meters a second. You might do some erosion damage, but I don't really see a huge issue with corrosion if you maintain the salt chemistry. If you don't maintain chemistry control, we can't do any of this. You lost chemistry control, and fluorine will eat anything, and chlorides won't be far behind.
Thank you. Has any thought been given to online salt processing and how to manage waste generated from this process?
Certainly, some folks are considering, online, salt processing. If you look at, for example, Flive Energy Inc. is considering reinstituting the processes that were done for the molten salt breeder reactor program. They have looked at the waste streams involved in that. That's part of some of the national campaign literature that has come out, is looking at some of the molten salt waste streams. I encourage you to look at some of the more recent reports that are coming out of PNNL. Some of the authors are folks like Brian Riley from PNNL or Joanna McFarland from Oak Ridge National Laboratory, which are looking at some of the waste streams that do include consideration of potential salt processing. And there are waste stream potentials. However, not every reactor does significant online processing, and they end up with very different types of waste depending upon what they're intending to do. People who do, for example, if you're just doing mechanical filtering, well, you have mechanical filters which are very hot, which don't look an awful lot dissimilar to resin beds. So I can't really say, whether any one particular design or any one particular set of processing has been adequately considered, because there is such variability, and the folks who appear to be coming first to the NRC, which Kairos has a number of topical reports ready for engagement, and Terrestrial appears to be about 6 months. Terrestrial Energy USA. 6 months or so behind. Neither one of them have extensive fuel salt processing.
Thank you. Is the nuclear data library in the present, such as JEFF, ENDF, JDL, etc., enough to be used for the neutronics calculation model of the MSR?
Well, the issue is do you have design optimization on there? And my answer is, of course, always negative no on there, because there are uncertainties in there, things. And we know things like the chlorine 37NP, there are uncertainties in the cross sections. On the other hand, is this adequately for safety calculations, and could we run a design based upon what we currently have? Answer is yes. the nice thing on the engineering stuff is there's a lot of margin in these reactors. We don't have to know things absolutely perfectly to have a useful and safe operation. Should we know more to improve, exactly what our fuel cycle is? Yes. I have no question saying that we should get some improved and decrease the uncertainty in some of the cross sections, but I don't think anything is currently limiting, someone in their application in terms of what's their safety on there. If we end up having to add a small fraction of a percent more fuel or less fuel over time, well, yeah, that's real. That's almost certain.
Thank you. I'm going to bundle a couple of these and see if we can clear out these last 4 or 5 that are here. The traditional thorium codes were developed based on water-based hydraulics and heat transfer correlations. I don't know, it's TH, so it's probably not thorium. The TH code used for MSR safety analysis has the salt-specific heat transfer correlated implemented. And then
there have been heat transfer correlations. Look at it's a single phase heat transfer. There are a number of heat transfer correlations and the differences within there. Go look at Becky Romanowski's PhD dissertation from MIT the last couple of years. It's got some good correlations in there. Prior to that, Grady Yoder, I think it was ICAP 2016, did a very good paper on heat transfer correlations and the status of knowledge. Yes, is there too much uncertainty in these? Absolutely. I think even in FLIBE, we probably have 5–10% uncertainty in some of the property data and the heat transfer coefficients. In the salts that are with fission products building in there, there is a substantial amount of remaining uncertainty in the correlations on there, and probably 30–40%. I would like to have it a lot better. I think that there's quite a great deal of room to doing heat transfer correlation measurements, and that being a useful thing to have to improve our designs. Because again, we have to put extra margin and extra conservatism in to accommodate the fact that our property data isn't as good as it should be. I would like to have much lower uncertainties on a lot of those numbers. But right now, what we do is we take what we have and we apply conservatism to the design.
Thank you. What is the impact of fission products on salt properties like fusion temperature?
Depends on how much is in there. How much have you built in? As long as it's a small amount, not much. If it starts being a substantial fraction on there, it changes the properties there. I mean, you become fissile fluoride, fissile chloride. But if you look at most of the thermal spectrum reactors, they're even very long periods of time. There's not huge buildup of the materials there. So there's not a tremendous impact until very long periods of time where you get very large amounts of buildup. Some of the fast spectrum systems have higher fractions of fissile materials in them, and this may occur sooner. There are also synergistic effects that you get things like lanthanum trifluorides, which displace some of the solubilities of the actinide trifluorides. And so you have to be aware of the impact of the decrease in solubility by building in fission products, and there's joint solubility differences. So these are phenomena which are known, but perhaps not known at the precision you would like to have them. Again, the technique tends to accommodate the unknowns in there is to generally have margin in your system. And then we need to have adequate knowledge of the fuel salt properties throughout the cycle. cycle. And yes, we'd like to have more knowledge of things like what's going to happen. Are we going to approach a solubility margin during before my next measurement of the fuel salt properties?
Thank you. Any thoughts regarding potential material fuel salts, accounting techniques from the safeguards viewpoint that could be employed by MSRs? Can we use a water-based thermohydraulics code such as TRACE for MSR safety analysis?
Well, TRACE has salt properties in it on there. They've been incorporated into some of the systems so that we can do thermohydraulics. But for safeguards analysis for a lot of things, I mean, the challenge becomes if I sample the salt in order to measure it, that becomes a removal path. And if you're looking at one of your models as well, if I keep sampling and keep sampling and keep sampling, do I divert stuff over years to get a small diversion path? I mean, but you're going to apply the traditional methods, key measurement points, material balance areas. I mean, it's not going to be different, in many ways than how you do a fuel cycle facility. And so those are questions about, where are my measurements? What should be there on there? How much? And so there's going to be a more intimate coupling between the operational history, because that'll tell you how much is being produced, and then the fuel system and the fuel cycle system. Because if you change the spectrum a little bit, or you change the amount of absorber, just going between a chlorine 35 5-base salt and a chlorine 37 base chloride salt will change the amount of plutonium you're producing on this, because it changes. And I think that anything which is going in and out of containment is certainly going to have to be measured. Is there a definitive answer to how are we going to safeguard any one particular design? The answer is no, we do not have that. Do I think that there is a reasonable path for safeguarding these designs? Yeah, it's going to be classic measurements of where are the fissile materials over time.
Thank you. Do people pronounce the acronyms like words? Would FLENAC use as primary fuel salt be acceptable in view of high solubility of plutonium and transuranics for fast neutron MSRs?
FLENAC has been considered by, there's one of the Russian groups has been looking at, because it's a it's a monovalent, you can dissolve more some of the actinides in there, and certainly, I forgot what his name, it's one of the Russian groups has been looking at FLENAC-based fast spectrum systems. And yeah, you can dissolve more actinides in monovalent instead of polyvalent fluorides, and looking at it for fast spectrum systems. If I weren't right here being pressed right now, I'd probably remember the design lead's name, but I can't right now.
Is it Ignatiev?
FLENAC is not radioactive. Well, it means potassium, and it's like bananas. They're radioactive. It's just natural.
Okay, last question. Have non-weapons grade fuel thermal MSRs demonstrated negative temperature coefficients?
There have been negative reactivity coefficients in designs, but we've only operated one MSR. So if you're saying demonstrated, meaning in a running system, well, MSRE used high assay MSRs, but it wasn't 93. It was, well, they were using plutonium and U-233 at the end, which were high assay for direct weapons usable, but the 33% or so enriched that they were running originally in MSRE is by definition above 20% on there. So that's the only demonstration we've ever had. So if the question becomes demonstration, we have not demonstrated anything about because we've never run a 2% enriched MSR. Certainly the 2% that is the terrestrial energies is making its case that they have a negative reactivity coefficient for a 2% enriched graphite moderated system, and that's they're currently undergoing licensing in Canada.
Great, thank you very much. That was probably 45, almost 50 minutes of Q&A, and we definitely thank you, David, for sharing your expertise and being willing to take so much time to address all of these questions. There's not a numbering system on this. When I get done, I can pull out a transcript, but that's got to be some kind of record number of questions that we fielded after today's presentation. So I think that shows a great level of engagement and interest in the topic. Thanks again for sharing your expertise.
Yeah, Bertha, I think we have 36 questions. It's a record, Dave. Thank you so much for your expertise. Thank you so much.
You're welcome. Hopefully this was informative and not too grossly controversial.
So thank you very much for also for the organization.
Oh, no worries. All right. Well, until September then. Thanks, everyone. Have a great day.
Thank you, Dave. Thank you, Bertha. Bye-bye, everyone.
Bye-bye.
Hey, goodbye.